Hi, good afternoon, everybody. Welcome to the 5 Ways with Hypervisor Networking talk. And thank you for coming towards the end of the summit. My name is Erez Cohen. I lead the cloud activities at Mellanox. And with me, Stig, I'll hand it to him.
Thanks, Erez. So Erez is VP of Cloud. I'm CTO at a small software consultancy in the UK. It looks like I pull rank on Erez being CTO, but we work as a team of 7 of us, and Erez, of course, works for a $1 billion a year company. So that's the scale of it. So upwards? Downwards?
Yeah, they will run.
Excuse me a second. That's not going. We'll do that. Do it the old-fashioned way. So what we're interested here today is the burgeoning use case for research computing on OpenStack. And really, this is something that has always been there. As long as OpenStack has existed, there has been an interest in using it for scientific computing. But we're going to look today at a very special and a very difficult use case, a little niche within that, which is this kind of tightly coupled scientific computing. So what we have here is a picture of fluid dynamics simulation. This is a package called OpenFoam. And we're looking at the particular requirements, the particular demands that these kinds of workloads place on an OpenStack environment. We're going to find out a bit about how it performs, how OpenStack delivers on those requirements, and also how the different ways that we can configure the very flexible networking infrastructure that underpins OpenStack and the differences that has on the way that this is performing. So this is one view of the way that OpenFoam is working. And when you look at it inside, so if we break it down, we can see this separate view, which is actually the processes that are working on the application workload themselves. So this is the timeline of the processes that are working. And what you can see is the different colors are annotations. This is a profile of how a parallel application, like a fluid dynamics simulation, is actually going about solving the problem. So each of these lines is one processor, and they're working together in a task. And you can see that they're synchronized. They're very tightly synchronized together. And the blue stages are compute, and the purple stages are communication time. So they're exchanging data about what they have simulated about their piece of the problem, like their wheel or the helmet or the other pieces of the mesh, the motorbike. Each of them is taking a particular piece, calculating its next stage, and then exchanging the data with the other workers. What you can see is the green spaces are where one of the workers has finished first and is idle and is just waiting for the other guys to come along. And that's vital. That's a key thing. So a tightly coupled application like this is very much moving at the speed of the slowest worker. And that is key to unlocking the whole problem with what's going on in a virtualized environment and how do we get performance out of virtualized networking. So we need to look at a nicely deterministic behavior, as well as high performance, low latency.
So before we go and talk about OpenStack networking, let's review a little bit about the different techniques to connect virtual machine into the network of the cloud. And here we are presenting 3 major ways. There are more subsets and variants of this. On the left-hand side, that is the first kind of virtualization networking that was created. It's device emulation. Basically, the VM had an emulation of a network device. At the time, it was E1000. It's a very popular Intel driver. And the hypervisor was emulating PCI, completely interfacing that virtual driver. And that worked. It was very flexible. Performance-wise, obviously, it wasn't that great. That model evolved into the para-virtualized environment. Para-virtualized means that it is still a software-implemented driver, but still there is a notion of virtual machine. The driver is not a general-purpose NIC driver like the E1000 that was in the past. Instead, it's a homegrown for virtualization driver that improves significantly the performance, and there were a lot of other enhancement to this model to accelerate. But in the end of the day, most of the deployments today run this model. We call it para-virtualized or para-virt, and the driver is virt.io. And in most of the deployments today, this is the default use case. On the right-hand side, I don't know if you can hear me, okay? Yeah. On the right-hand side, you can see SRIOV, or single root I/O virtualization. In single root I/O virtualization, we are doing something very different. We're looking at how do we virtualize the network adapter, not by having the hypervisor access it in the name of the virtual machine, but actually provide the virtual machine access to the NIC and virtualizing the NIC through PCI. SRIOV is part of the PCI specification. It's not limited to network. You can do SRIOV for any device, for storage or for GPUs in theory. But in this case, we're giving an example of a network adapter. In SRIOV, what we basically do is we kind of slice the NIC or the PCI device into multiple devices. We call them virtual function, or VFs. And those virtual functions are then passed through directly to the VM. And when the VM needs to send or receive data, it works directly against the NIC without going through the hypervisor. This approach provides the highest performance, and in addition, it exposes any additional functionality that the NIC may have, such as RDMA. We're talking about the interface. The previous slide was talking about the interface itself. I want to talk about RDMA because it is really important for the numbers that we will present later on. RDMA is a transport service, just like TCP and UDP that I'm sure you're familiar with. It's in the same layer, layer 4 of the networking stack. But unlike TCP or UDP, it was designed much later. If TCP and UDP was designed in the 70s, RDMA was designed in 99 or 2000 as part of the InfiniBand specification, and it is a much more advanced transport service. It provides not only send and receive operation, but also read and write operation. So one server can read or write to the remote machine memory directly through the network without going through the hypervisor to do it for it, or the kernel to do it for it. This concept of reading and writing over the network provides us a very interesting use cases that we can implement the application with. The other thing which is kind of built into this architecture of RDMA is kernel bypass, basically providing user space application and ability to read, to access the NIC directly from user space without things like DPDK that you are probably more familiar with. That provides us the low latency. This ability provides us latencies of about 1 to 2 microseconds, whereas if you go through the TCP IP stack, it will be probably not less than 5 or 6 microseconds. And the last thing is the full hardware offload. Unlike TCP and UDP that needs to go through the kernel and the packet needs to be composed in the kernel and then be set to the NIC, the RDMA can offload the entire network operation to the NIC and basically provide very high performance with zero CPU utilization. RDMA was initially started with InfiniBand and later on was moved into Ethernet. So now it is part of Ethernet. It is called RDMA over Converged Ethernet, or RoCE. There's a different API to use RDMA. It's called Verbs. But there are many applications these days that are using RDMA. It started in the high-performance computing, but these days distributed databases, machine learning, big data environments, all those kind of things already use RDMA natively. The important thing for our talk is to use RDMA, we need to expose the NIC itself to the guest, to the VM, because otherwise the abstraction of the virtual interfaces, virt.io and the like, kind of disallow using of RDMA. So SRIOV is required.
So we had a little project, and we looked at the ways that we can do networking today, and we picked 5. And we have our application, and we have some example workloads and some synthetic benchmarks to build up to those. And so we looked at these different strategies that are well established, some of them, and emerging are some of them. And we thought we'd compare them and see objectively how they perform for this very demanding networking environment. So we started with the one that pretty much you get by default if you don't actually specify any particular opinion, which is this combination of OVS and Linux Bridge. And then we looked at the alternatives that are emerging in terms of the newer capabilities in Linux Bridge and newer capabilities in building an OVS-only solution, which is OVN. And then we looked at how that compares with a couple of ways of doing offloads using SRIOV and this new emerging technology called ASAP squared. So I guess maybe a lot of you know this tool. This is Skydive, which is just a kind of helpful way of presenting the different ways these things are wired up. So this is a Skydive of a hybrid driver. So this is the OVS plus Linux Bridge. So because Skydive is very much more an OVS kind of tool, these are the OVS bridges, and these are the Linux bridges, which are kind of small in comparison. This connectivity shows a little bit about the underlying physical substrate of our system. So we have a gigabit Ethernet. We have a 10 gig Ethernet, which is behind a bridge for our control plane activities. And we have a 100 gig Ethernet, which actually is this one here. So this one is being used for tenant networking, and we're tunneling VXLAN traffic over this. So I think everyone probably knows how the hybrid driver works, but I'll just recap it quickly. So we use a combination in order to implement security groups. We use Linux Bridge and IP tables. And in order to then build kind of an SDN layer, an overlay on top of that, we use Open vSwitch. This is the standard. And it's generally becoming superseded nowadays by the enhanced capabilities that you can get in Open vSwitch. So it is the de facto at the moment, but may not be for a year or two more. The second strategy we took was to use Linux Bridge entirely by itself. So now we can use a VXLAN with Linux Bridge and use the firewalls as we were using previously. So this is this configuration here. We have our 100 gig Ethernet network there, and we have a number of VLANs which are strung off it. So this is a tenant VLAN here, and we can see the tap interface there going through a Linux Bridge and onto a VLAN tagged interface. So this is a VLAN network in this one, actually. So Linux Bridge gives us a configuration which is as simple as it can be without being too simple. It works well for the sort of research computing environments because it's not a very rich environment, but it's also fairly cut down in terms of the processor overhead that it imposes within the hypervisor between the guest VMs and the wire of the network. The next stage we had a look at was Open Virtual Networking, and this is OVN, which uses Linux Bridge. Uses OVS only, so it replaces Linux Bridge and the role that it had in the hybrid model with OVS connection tracking and a more sort of rich flow rules-driven environment. So this is something that is coming out now. It uses a couple of new technologies. So it uses it focuses on a different tunneling overlay called Genève, which doesn't have quite such the same level of support within the network cards as VLANs or VXLANs, and that comes through at the moment, but it has great potential as being a new, sort of more flexible, more extensible way of doing very powerful SDN capabilities. So in a little more detail, SRIOV, what you see with SRIOV is that all of this has nothing to do with SRIOV. SRIOV is what is not there. So in the SRIOV mode, we have virtual functions. This is one of them, and this is one of them. And I think there is a third one. The fourth one is not here because it has been passed through to a guest VM. So what you see with SRIOV is what has been taken out of the host hypervisor networking environment, and virtually in the VM, down to physically at the wire, the hypervisor has no sight of what is actually going on down there because it is a direct connection between the VM and the physical function of the network. So With SRIOV, we get very, very strong performance. We get something almost identical to physical layer performance that you would get in bare metal. It needs to have a network card that supports SRIOV, but a lot of good NICs will do that nowadays. And you need to have a little bit of extra effort in your OpenStack configuration in order to add SRIOV support. And then it's also, you need to do a little bit of knowledge within your guest creation in order to request that the ports that you are attaching to your VMs are SRIOV aware. So they have this thing called direct binding. This capability has a number of limitations, and the two biggies are that you can't do security. There's no firewalls because the hypervisor has no way of interposing any kind of security group rules between the virtual function in the VM and the physical function on the wire. And you can also not do live migration with this, although that is a technology that is being evolved, and I don't think that this will be true for very much longer.
Thank you. So we should show you the numbers and then get to the conclusion, but let me give you a heads up about the results. Anything that is software is not really good in performance. So virtual switches are a big bottleneck, be it OVS or Linux bridge, doesn't really matter that much. Mellanox, together with the industry, looked at how do we take the limitation of SRIOV and we gap them to provide both the high performance as well as the flexibility and the SDN notion. And one of the solutions that Mellanox is driving, or the underlying technology that we're driving, is called ASAP Square, Accelerated Switching and Packet Processing, which basically utilize hardware mechanisms within the NIC to offload virtual switches or virtual routers. So within the NIC, we have very advanced embedded switch. It is a real switch. It's not a software. It's not running in a CPU. And this switch basically offloads the data plane elements. It is a flow-based switch. There's hardware-based classifiers that can look at every packet in hardware and classify the packet into a flow. And then there is match action kind of tables that are fully programmable. They are very extendable. And there's a very large list of actions that we can take on the packet according to those tables. You can either steer them, you can drop or allow those packets. You can do header rewrites to implement routing or NATs and these kind of things. We can do encapsulation, decapsulation into overlay networks, be it VXLAN, MPLS, multiple tunneling technology, and many other things. So basically what we're offloading is we're offloading this classification action chaining of the switch. Now with this bare technology, with these building blocks, we can build many different solutions. We call this whole technology ASAP Square, but it can be resulted in fully offloading the OVS. And OVS is an example. Actually, it is also a product that we implemented with the community. But it can be other things. It can be also vRouter, and it can be also VPP in the future. So we can completely offload what we call full virtual switch offloads or ASAP Square Direct. We can partially offload, which is called ASAP Square Flex, and we actually can offload the application itself inside in the VM. So there are multiple ways we can use this technology. In this talk, we will focus around the full offload or ASAP Square Direct. In ASAP Square Direct, what we are doing is we are basically connecting the virtual machine through SRIOV to the NIC. And with OVS, we maintain the control plane, so all the SDN that connect into OVS or all the rules that are in OVS are maintained intact. But instead of running the data path in the kernel or in the user space with OVS over DPDK, we reflect the rules into this embedded switch, and then packet goes directly through the NIC, and the policy is enforced inside the hardware instead of in software. Now, to make this happen, we had to do a lot of changes in the various Linux kernel elements and OVS itself, and DPDK, and so on. All the work that was done is open source and standard. Actually, in Pike, you get OVS offload integrated if you get latest kernel 4.13 and OVS 2.8. And we had to create this new element called represent or ports. These are new type of ports inside the Linux that actually look like any other port, but instead of being passing traffic, they're kind of representing virtual function, and you'll see that in the next slide. So this whole technology was already implemented. We're kind of GAing that, and it is also integrated into OpenStack. Actually, the part of OpenStack integration was relatively simple. There were not a lot of changes to do. Probably the only main change was to allow OVS ML2 driver to bind into port type direct, which represent SRIOV, which in the past got nothing to do to OVS. This is the main change that we did. Other than that, a few things, and that part of OpenStack was really simple to do. Most of the work is done under the hood. Now, if we look at the map that was generated with ASAP Square Direct offloaded environment, you can think that there's no offload here because you can still see the OVS bridge here with the different port. But actually, those are not real. Those are the representation of the virtual function. So think about the VM connected to the NIC through virtual function that bypass the kernel and the hypervisor altogether, but there are representation in OVS so that it can program those interfaces and apply policies on them.
So we had a little experimentation here. And we put together a test system which was made available at Cambridge University in the development environment there. We have a 100 gig network, and we have a 10 gig network, and we have a 1 gig network. And we have 4 compute nodes and 3 control plane nodes, although actually we only really needed to use one of those. We built, using this system, 5 clouds. And you might think, when you look at deploying OpenStack, usually people will get some consultants in, or they will actually do a lot of reading up themselves. And it's very hard to conceive of a way that you could actually do 5 OpenStack deployments just for curiosity. So the only way that we managed to do this was by using OOO, this guy, and just using the flexibility that has and the momentum behind that project. And so we built up a OOO, RDO, and CentOS configuration, and then we changed some of the environment and manipulated the state of the hypervisor networking in those environment settings so that we created essentially 5 branches on our software-defined infrastructure code repo, and each of those was developed a little bit in each direction to give us the different network configurations. On top of that, I built up a bunch of playbooks for configuring the local environment and the application itself. And then also we cranked in a whole load of the standard set of hypervisor performance optimizations, which we're going to just sort of skim over here. And we'll go into in a little more detail on the networking after. So the machines we had, the compute nodes were 24 core with hyperthreading turned off. And the strategy that I came up with for the benchmarking was to create whole machine VMs. So in order to create a little bit of differential between the compute workload and the hypervisor cores, I made sure that there were enough cores to do a good deal of hypervisor networking and enough cores to do a good deal of work on the fluid dynamics simulation. So I made a 20-core VM, and I isolated the hypervisor processes from the workload processes. So then when we have 4 nodes running in this configuration, we have an 80-core or 80-node application. So I don't think we need to go into a great deal of depth on these things because those are well covered if you are looking up the ways to get optimized networking performance. And really, we want to look at some of the other pieces that we've been adding to this configuration. But I'll just skip through these. So we turned off hyperthreading to give us massive sort of straight line speed instead of greater concurrency. And we also turned off all the power states in the BIOS and configured the performance profile for sort of energy burning, highest clock speed, that kind of stuff. We separated out the workload from the hypervisor activities, and I think we've already covered that. So in the kernel, the sleep states are also disabled, so the cores are always on all the time. So there's no latency in terms of waking up. When you receive a message off the wire, everything is still going full guns blazing. Virtual CPUs are pinned to physical CPUs, so we have 20 CPU cores associated with 20 virtual cores, and we also pass through the fact that we have 2 NUMA nodes, and we also pass through the processor model and various other things too. So the graph here actually is a previous study I've done, and it kind of shows you a little bit of how these things can make a difference. So this is iPerf over time, and this was done with a 50 gig NIC, so the limit up there, that's 50 gigabits a second. And the different lines effectively represent this kind of continuum of convenience versus performance. So I'll take you through very quickly what the different lines mean and what each of them buys you in terms of performance versus the effort of configuring them. So this is the hybrid driver down at the bottom, and if you did no configuration at all, you'd get about a gigabit a second. And then if you do the BIOS optimizations, it goes up a tiny bit to the green line. And then if you change the kernel version, and a current Red Hat kernel will include these, but if you change the kernel version to one which includes the ability to do hardware offloads from the NIC on tunneled connections, then you get up from about 1.5 gigabits a second to about 11. Then if you turn off the hyperthreading, you get this purple line. And if you do the CPU pinning, you get a far more consistent line, but actually no massive gain in performance there. Ooh, what was that one? I think that was the NUMA awareness. And this line at the top is what you get if you use SRIOV. So on those NICs, we were getting about 42 gigabits a second, single stream TCP, one VM to another VM on different hypervisors. The blue line at the top is what happens if you go into the hypervisor itself and run the same test in bare metal. So you get about 46 out of a theoretical maximum of 48 after protocol. So a couple of the key things we did there are, firstly, to enable PCI pass-through, SRIOV capabilities, turn off all the power states, and separate out the cores for the workload. Now, this is a real-time Linux kind of hack, and it's probably not good for most applications, but it's good in order to give us a bit of separation here between the different cores and what they are doing. This was the favorite, though, being able to run a custom image in OO for our compute nodes, because we've done all these cranky things, is particularly when we install things like the software stacks for SRIOV and ASAP squared. They have no place, or they have no real relevance on the hypervisor, and we definitely don't want to be running on the controller nodes. We don't want to be running the controller nodes off just 4 CPU cores. So we have a separate compute node image with all of the optimizations baked in, and a separate controller image, which is just the standard over Cloud 4. And you can see the effect that has. So when we're running the workload, this is HTOP, and we can see that we've got 20 cores going flat out, and then the hypervisor cores actually are doing nothing at this stage because this is in the compute phase. But that is the observable consequence of applying these optimizations. There's other ways of seeing this. This is a kernel profile. This is a thing called a flame graph. And what we can see here, this is with the hybrid OVS and IP tables model. And what we can see is 20 cores working away up to this point. And then all of this stuff here, this is the time spent in the VXLAN, IP tables, hypervisor networking. So firstly, we've given away a good deal of fat on this side. But also it's interesting that one of the cores has very much less time on processor than the other 19. If we do the same thing in the SRIOV environment, you can see far greater regularity between the worker nodes. And this is very important when you think back to that first graph of the timelines and how operating as synchronously as possible in these tightly coupled compute environments really makes a difference. So we've got 20 cores across there, all doing pretty much, from this representation, pretty much the same sort of stuff. This guy at the end actually is KSM. This is the kernel same page merger. And if I'd thought about it, I'd have turned it off. But actually, it's kind of nice to use tools like this to profile what your hypervisors are doing when they're working, to understand what they're doing, which isn't the workload that they should be doing. So we have a few tests, a couple of fairly simple kind of synthetic benchmarks, and the OpenFoam fluid dynamics motorbike simulation as well. So I'm just going to take you through some of those results. And the first one we were going to look at is, what is the TCP performance when we're just going from one hypervisor and one VM to another hypervisor and another VM across the network? So this is a trip down through the networking stack and back up the other side. And what we can see is a huge disparity in results. And this is the number of iPerf clients, worker clients, going to one server. And this is gigabits a second going across one Ethernet link. So we've got 100 gig at the top. And what we can see is the hybrid driver is this purple line here. And it's kind of doing OK. We're doing a lot better than we were. We're around 20 gigabits a second, thereabouts. And Linux Bridge is actually topping it. So the simpler configuration of a Linux Bridge is giving us greater TCP throughput. This one at the bottom is OVN. And there are some interesting issues. So I wouldn't say that this actually is indicative of OVN's potential. But this is what I got on the test configuration in order to research for this talk. And there's several reasons why this is, and we can go through what those are. But one of the first ones was that it wasn't actually directing its traffic over the tenant IP network. It was going over the 10 gig NIC. It's achieving about 3 gigabits a second there. So I don't know if that is actually very significant. The hardware offloads are the two graphs at the top. So they're the star performers. That is ASAP squared with the red, and SRIOV with the blue here. So one of the interesting things that you can see from this graph with OVN is this is latency of packets. So we've gone on to a message passing benchmark where we're sending traffic from one server to the other backwards and forwards, called a ping pong. And for different sizes of message, we measure the time it takes to do a round trip from one to the other back again. And what you can see is that at about 1K, the OVN result jumps from about 40-something microseconds to over 100 microseconds. And that's one of the problems that we saw with this configuration and OVN. Given that it's using a different tunneling mechanism, it's using this thing called Genev, there wasn't hardware offloading support enabled or available in the Mellanox NIC. So at this point, we cannot do TCP segmentation offload. This is the idea where, in my guest, I can send a big chunk of data through a socket and not actually chop it into Ethernet frames. In the hypervisor, it will receive a big chunk, and it will process it as one thing. On the NIC, it will then, in silicon, in the hardware, it will packetize the whole thing into Ethernet frames. And this is why sometimes when you do a TCP dump, you wonder, well, why am I getting 2,000 byte frames? Well, this is why, because the NIC is actually behind the scenes doing the segmentation into Ethernet frames. And because we don't understand the encapsulation of Genev, we can't do that, and we get this horrendous spike in the latency, and it just goes off, up there, somewhere off onto the ceiling. Then the latencies we see for the hybrid driver is, so it comes in second, so that's about 26 microseconds for a message to go out to another client and back again. Sorry, it's one-way trip. So Linux Bridge did a little bit better. That's about 20 microseconds to send a message from one VM to another. And down at the bottom here, we have the hardware offloads, which all around 1 or 2 microseconds. So that is VM to VM. You can communicate in about 2 microseconds. The very bottom line is a similar cluster managed using Ironic with InfiniBand enabled, 100 gig again, and that gives about 1 microsecond. So that is the baseline to beat. If we look at the same data, but instead of looking at the time it takes, but look at the data rates we achieve, we get a similar kind of result in that we get the Genève was about 3 gigabits a second. And Linux Bridge and OVS Hybrid are kind of exchanging how they do. They're doing OK. They're not doing quite as well as any of the offloads. This is SRIOV, topping out at about 40. That's significantly under where it should be. And part of the reason for that is that Nova applies these fairly restrictive rules about being able to do core pinning, pass-through, and NUMA awareness, or SRIOV, pass-through and NUMA awareness, all together on the same VM. So given that we wanted to use 20 cores for our benchmark application, and the 20 cores were on 2 different NUMA sockets, Nova wasn't going to have this because we were asking for SRIOV, and it says you can only have that on 1 socket, on 1 NUMA node. So even though I wanted to use the entire VM, or the entire system for one VM for my workload, Nova wasn't letting me. So I had to turn off the core pinning, and that is why these numbers are punching below their weight. So this is ASAP squared, which is doing very well. And then at the top, we have the InfiniBand numbers, which out of a peak of about 100 gigabits a second is getting over 90. These results, I think, are the most important results of the whole talk. So this is this idea of all-to-all messaging. So we have all our compute nodes, and every one of them communicates with everybody else. So it's a massive flux of messaging going on. And this is a very, very stressful thing for any network. And a software network where you have a small number of cores in the hypervisor which are taking all the packets from all of the workload and processing them and sending that in the wire cannot cope with this situation. One of the ways it cannot cope is that it becomes overwhelmed by the CPU load. But then also it starts to build up a backlog, and it starts to discard packets. And then you lose the sequence, you lose the flow, and this has a massive knock-on impact. So what we've got here is essentially 2 cohorts. And to get them onto the same graph, I had to make a logarithmic scale. So each of these lines here is 10x. So we have about 1,000 times difference in the latency, in the time it takes to complete an all-to-all communication between all of the 80 nodes and all of the other 80 nodes. So that's a huge difference. And that really colors how everything else performs from here on. Because when we look at the fluid dynamics application, there's an awful lot of wide concurrency communication going on when the neighbors are exchanging data about each other's results. And that's reflected in the results that we see for the application. So this is the simulation of the motorbike. And what we've got here is runtime and partitioning time of the data mesh. What we can see is that all of the software bridges take over 8,000 seconds. And the offloaded methods all take about 60 seconds. It's a massive difference. And I think that the big message there is that if you want to do HPC in this kind of application with simulations that are using tightly coupled communication models, and you want to do it in an OpenStack cloud environment, if you care about the performance, then you need to use hardware offloads. And if you do use hardware offloads, then it is perfectly possible, and indeed completely doable, to get that kind of performance with very little additional overhead.
Maybe if I may just add, just before we get to the conclusion, so we're talking about pure HPC application here, but today many applications that are not considered pure HPC are using the same concepts. So if you look at machine learning and big data, they're having very similar communication patterns to HPC. So anything that is a little bit more advanced running on OpenStack, you'll probably want to be very careful on the network configuration that you're doing. Sorry.
So a few simple conclusions. Hardware offload on NICs is a game changer. And using that instead of software bridging inside the hypervisor makes a massive amount of difference in demanding networking applications. And these were the objective results that confirmed that to a far greater degree than I had ever imagined I would see before I started this experiment. Using RDMA instead of TCP adds further advantages. It lowers the CPU time spent in the kernel and in the hypervisor and not in the application. With ASAP squared, we get all of that performance and all of the offload, but we don't sacrifice security groups, and we don't sacrifice the other things that you get with SDN. And finally, if you really, really care about your performance, go ironic. So I'd like to thank Eres, who lent me the NICs for that, and the team at Cambridge for lending us the hardware to do the test. So thank you very much. Do we have any questions? Hi.
So the ASAP square is, what I understand is hardware accelerated OVS, that hardware accelerated from Mellanox switch, or?
No, the switch is in the NIC. So it's the same NIC that many has today, like ConnectX-4, ConnectX-5. In that NIC, there is actually a switch that we offload the virtual switch onto.
You don't need a vendor-specific Ethernet switch in the network, in your fabric. That can be anything.
Yeah.
We used a 100-gig switch, and it was a Mellanox switch.
But it doesn't require a Mellanox switch.
So can you give me any other example of the vendors which also use that kind of
technology?
Yeah.
Yeah. So the industry is referring to smart NICs these days as NICs that can offload elements from the host. Most of those smart NICs have some CPUs inside the NICs, and they are very, special and expensive, targeted to NFV workloads and those kind of things. Mellanox is a little bit different in the sense that it is all part of our standard NIC. It is done in ASIC, in hardware, rather than having a CPU inside the NIC. But there are many other solutions out there. There's Netronome, and there is Cavium, and there is Broadcom has this capability. The nice thing is that we kind of formed a general way to offload the flows and the rules into the hardware. We did it through open source consortiums, and so it should not be vendor locking from a software perspective, and then the difference will come in the NIC hardware capabilities and the performance, power, cost, and so on.
Thanks. Thank you.
Any other questions?
The hypervisor was KVM?
Yes.
Yeah, KVM.
Did you try anything else?
No, so as you can imagine, this took quite a lot of time, and still been working on that over weekends at nights because it's not as, so part of the things here, we could do maybe a little bit better. Stig mentioned OVN could have been probably tuned up better and other things, but we didn't go outside of KVM.
What is the feature set of OVS when it's offloaded onto the NIC? Is it the same exact feature set that the standard OVS has and running on Linux? For example, can I do lag between two OVS interfaces on the NIC as well?
Yeah. So as I said earlier, there are multiple ways to utilize this technology, ASAP square. What we did here is the OVS full offload, where we completely bypass the control plane, the data plane to the NIC, and there's other use cases where you go through OVS still, but you offload part of the pipelines. With the second one, the Flex, you get actually all the capabilities because you still go through the data plane in software. With the Direct, you may be limited depending on the hardware capabilities that you're using. So it depends on which hardware you're using. Specifically for Mellanox and specifically for ConnectX-5, you'll get AJ, you can do high availability, lag, but on a single NIC, not on multiple NICs. Single NIC 2-port, you can get SRIOV lagged. But there are other things that you cannot do. For example, stateful connection tracking is not supported right now. So looking at the packet sequencing numbers and stuff like that, many don't need that. But anyway, it is not available today. It will be available with the next generation of NICs. We are done. OK. Thank you very much, everybody. Thank you, Steve.